second speaker in this COLMEA. Gábor is a very well-known researcher in probability theory, especially as it applies to problem statistics and machine learning. So he's written some very nice books on the subject, on density estimation, on, well, there's one called The Probabilistic Theory of Pattern Recognition. That's a real classic and probably needs to be updated, by the way, but it's, I'll leave that to you. But it's a really nice book. And he's also got a book that some of you have seen in my office. I mean, those who are my students or have probably borrowed from me several times on concentration inequalities with Boucheron and Massat. And of course, that book's an outgrowth of their work on the field that really helped change its face. And he's also worked on many problems related to what we saw in the previous talk, and we're going to see now, which is what some people call combinatorial statistics. That is, you look at random probabilistic objects and you try to infer their parameters or properties of these objects from the object itself. Right? And I guess that's what we're going to be hearing about now, so without further ado.
Thanks so much, Roberto. It's always a pleasure to be here, and I'm going to try to behave so that I'm invited back. So today I will talk about a bunch of results in an area that we call network archaeology. I will explain where the name comes from, what it means. And I will go through a few results that were joined with some of these people. Luigi, he was here 2 weeks ago. He's at McGill University. Seb is at Microsoft Research in Seattle. Luke was here last week. He's also at McGill. Vasiliki was a PhD student. She's now a postdoc at the Hebrew University. Simon is here, sitting there. He's a PhD student. And Francisco is another PhD student back in Barcelona. OK, so, so what is this network archaeology business? So we are talking about networks that grow in time. Okay, so you can think about social networks. That's a good example. When new users come, they join the network in some way, and then the new connections are getting established. But you can also think about epidemiology, right? Where disease is spreading, and it's forming a network, rumor spreading, computers networks. I'm not going to talk about applications, but you can make up your favorite story as we go. Okay. So the statistical problems that we are interested in are when there's a growing network, and sometimes these networks are gigantic. Then we observe such a network. We see a present-day snapshot of this network, and we would like to say something about the past of this network. Okay? So, for example, who were the original vertices? What did this network look like a long time ago? Are the vertices that seem to be influential now, have they always been influential? Okay, so this type of questions. There are many nice questions that you can ask, and I will concentrate just a couple of them. One is called the root finding problem, and the other is called the broadcasting problem, and I will explain later what these mean. So when we want to have fun with statistical problems, we need a nice probabilistic model. And the nice probabilistic models that we focused on are uniform and preferential attachment models. So these are really the simplest kind of growth dynamics that you can imagine. The uniform is really the simplest. When a new vertex arrives to a network, it just chooses one or several vertices uniformly at random and attaches to that vertex. Okay? So in the special case, when only one vertex is chosen, then the resulting network is a tree. Okay? And the large part of this talk, I will only talk about trees, and then we will also discuss a little bit more complicated networks when more than one vertex is chosen uniformly at random. Okay, so that's the uniform attachment model, and the resulting tree, the uniform attachment tree that's been studied for a long time by probabilists. It's called the uniform random recursive tree. Okay, so this tree starts with a single vertex. When a new vertex arrives, it attaches to it. when a third vertex arrives, it chooses one uniformly at random, attaches to it, et cetera, et cetera. Okay, so this is how the uniform random recursive tree or the uniform attachment tree is formed. A little bit more refined model is this preferential attachment model here, where when a new vertex arrives, it chooses a vertex at random, but the distribution is not uniform. Now, more popular vertices are more likely to be attached to. What does popularity mean? It means that it has a large degree. Okay, so in the simplest version, the probability of a vertex to attach to is linearly proportional to the degree of that vertex, to the number of connections of that vertex has. Okay, so this is the preferential attachment model. This became very famous in the analysis of social networks because for some interesting reason, this really simple random dynamics reproduces macroscopic qualities of networks large networks that's been observed in social networks. So for example, big hubs are being formed, power law degree distribution, and then the many other nice features of large networks can be described by really simple local dynamics like a preferential attachment. Okay, so I will focus on these simple models. Okay. Please interrupt me anytime there's something that's unclear. Okay, so I already said that the uniform attachment tree is called the uniform random recursive tree. Even the preferential attachment tree had been studied way before the preferential attachment model was invented, and this is called the plane-oriented random recursive tree for reasons I'm not going to explain, but this tree had been known in probability theory. Okay, so we know a lot about these trees, and that's going to be very useful for us. All right. So the first problem is we call it the finding Adam problem, okay, or root finding problem. Vertex number 1, we call it Adam. Okay, so we would like to find Adam. Okay, so we observe in the simplest model, we observe a uniform attachment tree, maybe a very large one, and we would like to find which is vertex number 1, which is the vertex who started this whole thing. Okay, of course, Adam and Eve are indistinguishable. Okay, so just finding Adam is hopeless. So we have to define the problem a little bit more refined way, and the way we formulate it is that the statistician, us, we can choose a set of vertices, okay, and this set can have some size k, and what we would like to have is that it is guaranteed that with probability at least 1 minus epsilon, the root belongs to this set, okay, and now the question is, okay, so how large does this k have to be? Okay, what's the smallest possible size of a set that's guaranteed to contain the root with probably 99%? Okay, and how does this depend on the size of the network, and how does this depend on this probability epsilon that we allow? Okay, these are called confidence sets. This set of candidate vertices for the root. Okay, so this is the finding Adam problem. Okay, this is what a uniform attachment tree looks like on 50,000 vertices. Okay, so that's the question. Where is Adam? Which one is this? How many vertices do we have to pick from here such that we can say with high confidence, with confidence in 99%, that one of them is Adam? Okay. So so these results that I'm going to sketch are in this older paper with Seb Bubek and Luc. So what we found, perhaps surprisingly, it was a bit surprising for us, is that in both uniform and preferential attachment models, the number of vertices is independent of the size of the network. So finding Adam in this network is not easier than a network 100 times bigger, okay? Or not harder than in a network with just 100 nodes, okay? And it only depends the size of the confidence set only depends on epsilon, the probability of error that we allow. Okay? And the other surprise was that finding the root in a preferential attachment tree is strictly harder than in a uniform attachment tree. And that was surprising to us because preferential attachment trees tend to have these hubs, these vertices with gigantic degrees, and one would think that that would make finding the root easier, but actually it doesn't, and I will try to explain why. Okay? So here's the first idea that comes to mind is that old vertices have had a long time to collect more connections. So let's look at the vertices with highest degrees. Okay? Now, for the root, it's very easy to understand what the degree is, right? Because at time 1, Eve will connect to Adam, and the next guy with probability 1/2, and the next guy with probability 1/3. So the number of connections of the root, well, the expectation is ln n, and it's really concentrated. There's a nice central limit theorem, so this is really the root of the vertex. The degree of the root is really about ln n. Okay. But it turns out that the maximum degree in such a model, and this had been known, a result of Luc, old from the 80s, shows that the maximum degree is actually a factor higher. It's log base 2 of n. And there are now nice results by Laura Slava. She was a PhD student of Luigi, who showed that, in fact, the vertex with high degree is actually pretty far from the root. Okay? So using these results, it's not very difficult to see that if we sort vertices by degrees, then the root will be very far down. So certainly, it's not going to be among the top constant number of vertices. Okay, so sorting by degrees, it will not work. Okay, in preferential attachment trees, it's a different story, and it does work. We will come back to that a little bit later. Okay, so here's a really simple method that actually works. This is, when we wrote this paper, we didn't know this expression. This is called the Jordan centrality. So for every tree, there's a vertex. This is called the centroid of the vertex that has the property that if you remove it, then the tree decomposes into a forest of components at most half the size of the tree. Okay? Every tree has at least one and at most two such vertices. These are called the centroids. Okay? And we can define the centrality of every vertex by looking at a vertex and now looking at all these subtrees that hang off that vertex, right? And we look at the largest of the subtree and the size of that, okay? So the centroid is the one that minimizes the size of the largest subtree, right? That's somehow there. If you look at a leaf, then it only has one subtree and it has size m-1. So that's very, very non-central. Leaves are the least central in this sense, and the centroid is the most central. Okay, so now the proposed method is let's just sort vertices by their Jordan centrality and pick the k largest. Okay, and then what we can prove, and this is really not difficult, is that if k is something like 1 over epsilon, well, it's 11 log 1 over epsilon, but morally, let's just say 1 over epsilon, then the root is contained in the k most central, is among the k most central vertices with probability 1 minus epsilon. Okay, yeah?
These k vertices are all very close together.
And they form a tree actually, yes. Okay, yeah, and that's actually important for some reason coming up later. Yeah, it's also nice that this can be computed very quickly, partly because of this. So in fact, the centrality is along paths is a monotone quantity. Okay, so this can be computed really quickly, and so the idea of the proof, I'm not going to go too much into it, is that if these subtrees they evolve as simply polyaurns, right? Because when a new vertex arrives, it will attach to one of these subtrees with a probability that's proportional to the size of that tree. exactly proportional to the size of this is the well-known Polya-Earn model, so we can just use classical results from the asymptotics of Polya-Earn to get this. Okay? All right, good. Now, this is what I already said. Now, it's also easy to see that with this method, we cannot do better than 1 over epsilon. Okay? And what's the reason? Well, the reason is that in a uniform attachment tree, the root will be a leaf with probability bigger than epsilon for time about 1 over epsilon. Okay? Right? Because the probability, let me just draw here. Right? This is the root. After 1 step, it's still a leaf. Now, after 2 steps, it will be a leaf with probability 1/2. And now, in the next step, this has to be avoided. So the probability that it's still avoided is 1/2 times 2/3, and so on and so on and so on. Okay? So the probability that after k steps, well, I don't know why I wrote 3k here. After some 3k steps, it's still a leaf is 1 over 3k. Okay? Oh yeah, so we need this because we know that in such a tree, about half of the vertices are leaves, so we won't be able to tell them apart. Okay, so the root is still a leaf. So this means that with this particular method, that simple analysis was optimal up to a factor of log 1 over epsilon. Okay. Now, a natural question is that, okay, can we do better than this really simple Jordan centrality? Okay. All right. So as statisticians, we know what the optimum method is. That's maximum likelihood. Okay. We just have to determine what it is. Okay, so we observe this big tree, right? And now for every vertex, we can assign a likelihood. So what is that likelihood? That's the likelihood that that vertex is the root of this shaped tree. So that is proportional to the number of recursive labelings of this tree. What's a recursive labeling? Is just an assignment of indices to the vertices that are monotone along paths. Okay, that's a recursive labeling. Okay, so we can imagine for every vertex that was the root. The number of different ways this tree could have been produced by that vertex being the root is proportional to the number of recursive labelings of that, and we can count that. This is the number. Okay. So what is this? So this thing here is so for each vertex, when we imagine that this vertex u is the root, so this is u, and for any vertex v, there's a unique path that connects it to the root, and now we look at this subtree. This is the tree T u v down, okay? That's this guy, okay? So for every vertex, we can look at this subtree that looks away from the imagined root, okay? And we look at the size of this tree, and we take the product of this over all v's, okay? Before, instead of taking the product, we just among the neighbors, we just took the largest one, okay? But now we go down every path, and for every vertex, we take this subtree and we multiply them together. This is another centrality measure, okay? And there's this annoying automorphism factor that I didn't even write down what it means. It involves all these automorphisms of these subtrees that hang off, okay? But this is the maximum likelihood. So we know what the optimum way is. We have to, in order to minimize the size of the confidence set, we have to sort vertices according to this function. Okay, all right. This is good to know, but how can we analyze this? Well, we can use this to derive silly lower bounds. Okay, because there are some very simple situations when we can say that the root is certainly the least likely. Okay, so for example, if the tree starts with a long, long, long path, and then it looks normal, then we can prove that the likelihood that assigned to 1 is the worst in this tree, and then this cannot possibly work, and this still has some probability. And if we work that out, then we get that if k is smaller than e to the square root of log 1 over epsilon, then there's no hope of finding the root. Okay? This is a really silly lower bound, but we don't have anything better. So this is one of the open problems that I wanted to mention, to try to get a better upper bound, a better lower bound. Okay? Okay, but we can also try to analyze this. Okay? Now, because of this automorphism factor, we didn't know what to do with it. We just dropped it and said, okay, this is also a centrality measure. So let's just try to sort vertices according to them. Okay, so again, this is just the product for each vertex. We look at the product of all these subtrees that look away from that vertex. Okay? And it turns out that this centrality measure actually had been defined before, independently of us. This is called rumor centrality. They were interested in finding the source of a rumor. And after we analyzed it, and after we published our paper, a few years later, Harry Crane and Zhu from Rutgers proved that in fact, if by removing these automorphisms, the ordering doesn't change. So in any tree, if you look at the order of the vertices according to these two measures, we get exactly the same ordering. So dropping this automorphism factor was the right thing to do. It just made things simpler, and it doesn't change anything. Okay, it's kind of surprising, and it was nice. And then what we got for this is that this method is actually much better than the one based on Jordan centrality, because it works already when k is larger than something like e to the log 1 over epsilon over log 1 over epsilon. So this is much better than any power of epsilon. Okay? Before we had something like 1 over epsilon. Now we can do better than 1 over epsilon to the 1 over million. Yeah? So this is better than that. Yeah?
This doesn't contradict your construction of the 1 epsilon, because that was only for
that was only for that. Yeah, right. So because some leaves are actually more central than other leaves, right? Which the Jordan centrality doesn't take into account. Okay, so what about preferential attachment? We had a result that said that if k is bigger than 1 over epsilon to the 4th, then it already works. Again, the same Jordan centrality method works. Again, we have an earn process, but now we have to count not vertices but edges. Okay, so in linear preferential attachment, again, the sizes of the subtrees grow as a polyurn, but with a slightly different dynamic. Okay, so using that, we proved that the root is contained so we can find a set of size 1 over epsilon to the 4th that contains the root. And this was by Banerjee and Shankar Bhamidi. This was improved to 1 over epsilon squared, essentially. Okay? And this 1 over epsilon squared is much worse than 1 over epsilon. Even 1 over epsilon, or it's really much worse than this bound, right? That we got for uniform attachment. But it's you see, what's the reason? Why? First of all, why do we get here 1 over epsilon squared and not 1 over epsilon? Well, you see, in preferential attachment, the probability that the root remains a leaf for a long time is much bigger than in uniform attachment, right? Because if Eve attaches to Adam, now if the next guy attaches to Eve, then all of a sudden, Adam is half as popular as Eve. So the next guy is more likely to attach to Eve, and so on. Okay? So the probability that after k steps, the root is still a leaf is 1 over square root of k. Okay? So that means that if we order by Jordan centrality, then the method has to have k larger than 1 over epsilon squared. So if you just look at this Jordan centrality measure, then preferential attachment is much harder. Okay? Okay, but that's just preferential attachment. But we can also prove that for any method, you cannot do better than 1 over epsilon. Okay? And the reason for that is simply because one can show that this type of picture is quite likely to happen. Okay, so what is this? The root is still a leaf for a long time, okay, for about 1 over epsilon squared steps. And Eve is a hub with square root of the number of so the degree is square root of the number of vertices. And many of them, a constant fraction of them, are leaves. So that means that the root is indistinguishable from all these leaves. Okay? So if you put all these things together, then you see that no method can do better than 1 over epsilon for preferential attachment. Okay? And this is the reason why I said that finding the root in a preferential attachment tree is strictly harder than finding the root in a uniform attachment, which, again, it was a surprise to us, but now we know what happens. So here's the summary of what I told you. So, so finding the root in the uniform attachment, the optimal value of k is independent of n, right? And the dependence on epsilon is between these two numbers. And I believe that the upper bound is tight because we had to work hard on it, and here we didn't work too much. And it just doesn't feel right. So I think this might be the truth, but I have no idea how to prove it. For uniform attachment, it's between 1 over epsilon and 1 over epsilon squared. But just maybe a week ago, this paper came out. A group in Orsay closed the gap, and they showed that 1 over epsilon is an upper bound for preferential attachment. And the solution is very cute. What they show is that we have to look for pairs of connected high-degree vertices. Because what they show is that if Adam has a low degree, then Eve must have a high degree. Okay? So in a clever way, we look at pairs of vertices such that one of them is very high degree and the other is moderately high degree. And among those, the root will be there. Okay? Yeah? Not necessarily, but with high probability. It's sufficiently high probability that happens. Okay? It's a very nice, short, very nice paper. Okay? So it's a nice idea. So now for preferential attachment, we know that what the right answer is 1 over epsilon. Here we still don't know. Okay? Okay, so that's what I wanted to say about okay, there's still time. About root finding. There's some related work. Let me skip it because there's a lot. Maybe I should mention this because Alan was a student here, and we had this paper, and other people also considered when the network doesn't start with a single vertex, but with some small tree. And now you want to either find it or test what the tree might be. Okay, so there's this nice result by Bubeck, Eldan, Mossel, and Ratz, who showed that in a uniform attachment tree, the network will always remember the initial configuration, whatever it was. So there's a statistical test with non-trivial probability of error that can tell apart whether a tree started with a path of 3 vertices or a little star on 3 vertices. Okay, I guess not 4 vertices. Okay, so we can tell them apart, and then yeah, so there are some of there's a bunch of results on this. This other paper is the analog for preferential attachment trees and so on. Okay, so now in this second part of the talk, I will talk about what we call the broadcasting problem. So here the vertices have colors. Okay, So the vertices, again, the tree in the first part I will talk about only tree. So the tree is grown again by either a uniform or preferential attachment process, but the vertices can be Flamengo or Botafogo supporters, okay? And that's their color, okay? And when a new vertex arrives, it attaches to a parent, and of course you're a good child. You will take you will follow the same theme as your parent, okay? Unless you're a rebellious child, in which you will go to the other team, okay? And that happens with some mutation probability Q, okay? So this is how the colors of the vertices are assigned, and of course, there's also Vasco and other teams. So you can consider this with more than 2 colors. It's fine. I'm just gonna stick to these 2 colors. Okay. All right. So the classification problem is now that we observe this tree without labels, but with the colors. Okay. And then we would like to know what theme did Adam support? Okay, what was the color of the root? Okay, so that's a classification problem that has an optimal probability of error that depends on this mutation probability and on the size of the network. How does this depend on N and Q? Okay, of course, now after what I told you, it's not a big surprise that it doesn't depend on N. It depends on Q. Okay, so we wanted to find out how. So this is how the tree is constructed, right? This is the root. He was a good guy, Botafogo guy. And then number 2 was connected to it. Number 3, they're all good children, right? Number 4 was a rebellious child. It's a descendant of 2, but changed colors, okay? Number 5 was good. Number 6, again, is rebellious, and so on, okay? And then what we observe is this tree. This tree with these colors, and the question is, what's the color of the root? Okay? There's a more difficult version of this when only the leaf colors are observed. Okay? So in broadcasting, often we don't know these are species, right? These are extinct species, and these are the ones that are extinct and extant species, and we can only see what happens with the ones that are alive, and we still want to ask the same question. Okay. All right. So this is stuff from this paper with Luigi, Luc, and Vasiliki. So the first trivial observation is that the optimal probability of error is at least Q half. Why? Because with probability Q, Eve is rebellious, changes themes, and then from then on it's just a coin flip. We don't know what to do. Okay, the best thing you can do is just flip a coin. Okay, so on that event, it's hopeless, and that happens with probability Q. So the probability of error is, the optimal probability of error is at least Q half. We know what the optimal classifier is, right? Because we can just compute for every blue vertex the likelihood that that vertex is the root, and we can do it also for red vertices, and we can compare, right? And this was just the likelihood. But okay, good luck with analyzing this root. We don't know. So, but there are really simple methods, and some of them we can immediately use from what we know for root finding. Let's just localize the root. Okay. Here, epsilon, we choose epsilon any way we like. Okay. So pick an epsilon, localize the root with right. Find a set that contains the root with probability 1 minus epsilon, and go with majority. Okay. So the probability of error of this is at most, well, epsilon is the probability that we miss the root, and the probability of error of the majority is at most the probability that there's at least one color change in this set, and that can be upper bounded simply. So if we plug this thing in, then and we optimize in epsilon, that we get that the optimal probability of error is, for the uniform attachment, is at most q to the 1 over log 1 over q. Okay, And the preferential attachment is Q to some other power, which is not 1/4 anymore. I think it's 1/2 now. Okay, so we get something better. So this is a constant. It's not quite linear, right? But it's close to the trivial upper bound. But we can do better. And the crucial observation for doing better is that what really matters here is not to find a small subset that contains the root, but we would like to if we find a vertex that is really close to the root, that's enough, right? Because if you're guaranteed to be close in graph distance to the root, then we know that there haven't been many chances for color change, okay? The root has many, it has log n connections. It suffices to find one. Okay? So in particular, if we pick a vertex whose distance to the root is capital D, this is a random variable because V is just a random vertex, then the probability that the chosen color is different from the root is, well, there have to be an odd number of color changes. Right? So our method is just find this vertex and go with the color of that. Right? So there have to be an odd number of color changes between the root and this vertex, and that is bounded by Q times the expected distance. Okay? So what this shows is that if we can find a vertex such that we can guarantee that the distance in expectation is bounded, then we have a linear upper bound. And this is really easy, because we can just go with the centroid. Okay? Remember the centroid, that vertex that has the property that if we remove it, then the tree decomposes into a forest such that each component has size at most and half. With high probability, there's only one of them in a random tree. And well, this was after we published the paper. Well, after we submitted the paper, we found this nice result of Moon, who showed that the expected distance is actually 1 asymptotically. Okay? We proved that it's smaller than 2 or something. But and there's even a similar result now by Wagner and Durant for preferential attachment trees, so we can do the same for preferential attachment trees. Here's the reason why the centroid is really close to the root, because suppose that the centroid is far from the root. Okay, so this is the centroid at time n, right? At the time when this was born, if this distance is t, then there are t vertices in this big red blob. And there's only one vertex in this green blob. And then we know that after time n, more than half of the vertices should end up here. But these blobs evolve according to a polyurn, where this urn starts with 1 ball and this starts with t balls. Okay? And the probability of that is exponentially small in t. Okay? So in fact, the distance is bounded by an exponential random variable. And in particular, the expectation is finite. So what it follows that in the uniform attachment model, now we can nail the optimal probability of error. This gives just Q. Okay? And we know the trivial lower bound is Q half. We can improve the trivial lower bound a little bit, but we couldn't close this gap. So we don't exactly know the right constant, but it's okay. And moreover, another question that people study is can we do better than random guessing? Okay? And this shows that we can do better than random guessing whatever Q is. Even when Q equals 1/2, we can do better than random guessing. When Q is less than 1/2, then this is smaller than 1/2. If Q is 1/2, that means that the color of every vertex is just a coin flip. But then we can use our finding Adam method to find just a constant number of vertices that contain the root, and there the majority will be a little bit better than random guessing. Okay, so we can do better than that. What happens when only leaf colors are observed? Well, even then the probability of error is a linear function of Q, and the reason is that is that in a uniform attachment tree, there are always leaves very close to the root. In fact, the root typically has the number of children of the root that are leaves is a Poisson 1 random variable. Okay, so there's in expectation there's one immediate descendant, and but there will be two with very high probability. There will be a leaf within distance 2 with very high probability. Okay, so then what we can do is just find the centroid and find the centroid is of course not a leaf, but we can find the nearest leaf to the centroid. The nearest leaf to the centroid. So that distance is small, and the distance, therefore, the distance to the root is also small. So we get that, and we can also show that this will work better than random guessing as long as Q is less than 1/2. If Q is 1/2, then there's nothing we can do because the root is never a leaf with very high probability. So in that case, it's we just observe noise. Okay. All right. We also studied a really simple rule that completely disregards the graph structure, and we just count Botafogo and Flamengo subrouters. Okay, so what's the who's in majority? Yeah, and it turns out that this also for small q, the probability of error of this really simple rule is also a linear, bounded by a linear function of q. And moreover, the simple majority rule will work better than random guessing as long as q is smaller than 1/4. Okay? But when q hits 1/4, then random noise will take over. Okay? So the reason for this is well, you can write down, it's kind of an earned process, the number of colors with random replacement. And if you analyze this, then you will find that macroscopically there will be about 50 and 50, red and blue guys. But then there will be a little bit of bias, and that bias survives when Q is beats the random noise when Q is smaller than 1/2, but when Q is at least 1/4, when Q is at least 1/4, then the random noise will take over. Okay. All right. So just for fun, we also looked at the case when Q is bigger than 1/2. There's no story I can find. There's no application that I can make up for that. But even in that case, we can show that the optimal probability of error it beats random guessing, unless Q equals 1. If Q equals 1, that means that with probability 1, Adam and Eve are now, one is blue, one is red, and then they are indistinguishable. So there's nothing we can say. But in all other cases, and actually this was the hardest result of this paper, to prove that when Q is bigger than 1/2, then we can still guess the color of the root. Okay. All right. So in the remaining 10
minutes past 5.
Oh my God. Okay, no, I'm not gonna go that far. Okay, I won't. Okay, so in the remaining time, I wanna talk a little bit about extensions from trees to more complex networks. Okay, and the next simplest thing that we could think of is we call them random uniform K-DAGs. Okay, so this is a model in which when a new vertex arrives, it chooses not one parent, but K parents, uniformly at random, let's say, with replacement. It doesn't really matter if it's with or without replacement. But for concreteness, let's say it's with replacement. Okay? So we start with one root, and when a new vertex arrives, it chooses K parents and connects to them. Okay? So Eve will connect to Adam with K parallel edges, but we will collapse parallel edges such that just to avoid trivialities. Okay, and this network is also just the union of K independent uniform random recursive trees, right? Laid over the same vertex set. Yeah? Okay? Right? Because at each time, we just choose k vertices. All right? So can we find the root vertex? That's our first question. Can we find Adam? So this is written in this paper with Simon and Francisco, just accepted. Thank you, Rob. So here, the difficulty here is that all these nice centrality-based methods that we use for trees go out of the window because now we don't know what Jordan centrality is. We don't know these other centrality measures. So then our first idea was to look for surely there will be more triangles around the root, right? Than for a late coming vertex. Okay. And indeed, if you count the number of the expected number of triangles that the root participates in, that goes to infinity. The problem is that also goes to infinity for very late coming vertices. Okay, so that's not good enough. Then we thought that okay, maybe let's look at something more complicated, a diamond, yeah, which is just a 4-cycle with a chord in it. For that case, we could show that late coming vertices will not participate in any of these. It's also true that the root, the expected number of vertices of these things that the root participates in goes to infinity. However, there is no concentration. So with positive probability, the root is in none of these. Okay, so the second movement method doesn't work and doesn't work for a reason because it is just not that. So then what we found in the end is that these things that we call double cycles actually work. So what's a double cycle is just we have two vertices that may be collapsed into one with 3 disjoint paths connecting them. And these red vertices, we call them the anchors. Okay, so we call these double cycles. And so what we're gonna do now is that we take a carefully chosen size of these double cycles and list all of them and look at the anchors. Okay, and what we can show is that the root will participate with high probability. The root will participate in at least one of these. And no late coming vertex will be an anchor of any double cycle. Okay? So in particular, what we show is that right? So K and L are the lengths of these two cycles here. Okay? So this is a KL double cycle, and we limit the length of both of these cycles by m, and this m will be chosen carefully as log 1 over epsilon divided by k. And what we can show is that with probability at least 1 minus epsilon, the root is in one of is an anchor of such a double cycle, and the number of these double cycles is bounded, okay, independent of n. Okay, so if we optimize the constants, then what we get is that the number of candidates is at most this thing here. So there's a 1 over epsilon here, which is already worse than what we had for the best thing for the case of k equals 1. Yeah. But things get much worse when with this factor. There's this log 1 over epsilon to the power of log 1 over epsilon. Okay, so if k is 2 or 3, this is huge. Okay, but that's the best we can do now. Okay, so at least this is independent of n. Okay, so this is just okay. Let me skip this because there's other stuff I want to talk about. This was just some idea about the proof, but basically, oh yeah. We can also extend this to a different model that was introduced by Cooper and Fries when they wanted to model large They wanted to model the internet, basically. And this is a method, this is a big family of models with lots of parameters. If we choose the simplest one that we call the uniform random model, then the same result is also true. And basically, the key in the analysis in both cases is that we can show that both of these models, these k-DAGs, uniform k-DAGs, and these Cooper-Friis random graphs. So these Cooper-Friis random graphs, this is also very nice. So at each time, either we add a vertex that attaches to a uniform node, or we add a uniform edge to the existing vertex among the edges that are not there. Okay? And then each time we flip a coin, we either add an edge or we add a vertex. That's this uniform code. So both of these models can be dominated by a certain inhomogeneous Erdős-Rényi random graph in which we can do all the calculations. Okay, that's just on the technical side. Okay, and so the very last topic is now the extension of the broadcasting problem to these k-DAGs. Okay, so remember now in this case we have k roots. Okay, so there's the whole Old Testament, and they all have chosen a theme, red or blue. Okay, k is odd. Okay, because what we are trying to guess is the majority of the original k guys. Okay, and now when a new vertex arrives, it chooses k vertices uniformly at random. Okay, and now it looks at the colors, but the colors come through a noisy channel. Okay, so each of these colors flips with a certain probability p, and now this child takes the majority of these. Okay. Right? So we connect to k vertices. Each of the colors is changed with some mutation probability p, and we take the majority. Okay? So the problem is now that we observe the random uniform k-DAG with the vertex colors, and we would like to find out what was the majority color among the k original nodes. Okay? So this paper is in the works. It's almost done. And what we studied in this paper is just the simple majority rule. So disregard the structure. Just let's see what happens. Okay? We know that in the case of k equals 1, the majority rule works well as long as the mutation probability is smaller than 1/4, but it stops working when the mutation probability is bigger than 1/4. Okay? So So we can, the number of vertices, this is the proportion of vertices. Proportion of red vertices is Rn. The proportion of blue vertices is 1 minus Rn. Okay? So we can write down, so initially, we can write down kind of a generalized, randomized, nonlinear polyRn type of model. Initially, there are k times r k red and k times 1 minus r k blue balls in this urn. And then at each time, we draw k balls uniformly at random without replacement, right? These are the attaching vertices. The color of each ball is flipped independently with probability p, and then a new ball is added to the urn, which is just the majority color of these flipped guys. Okay, so that's our urn process, and B and Mudge, this is the majority color at time n. Okay, so the probability of error is that the majority at time n is different from the majority at time k. Okay, so we would like to analyze this probability. In particular, the question is, for what values of this mutation probability do we have that there's still signal? So we do better than random guessing. Okay? So the first step in this analysis is to understand the behavior of these random colors. Well, actually, it's not just the first step, it's the whole thing is in there. So this is, there's this stochastic recursion. The proportion at time n plus 1 is the same as time n, and it increases if the new ball is red. Okay, And the proportion increases by this much. And now the probability, given the past, the probability that this is red is just the probability that, that this binomial is a majority, right? Okay. So if the expected increase is this function, g of t, and you see this is kind of a stochastic dynamical system. These are also called reinforced random processes, and this type of processes had been studied quite a bit, so it's not a surprise. And what matters is the zeros and the nature of zeros of this, okay, of this expected increase. And in our case, depending on the mutation probability, there are two types, well, actually basically two types of behavior. So in all cases, this function is convex under 1/2 and concave after 1/2, okay? But it starts at positive, it ends at negative. But when the mutation probability is small, then it actually crosses 0 here and crosses 0 here, okay? So you see, if at some time the proportion, let's say the proportion of the balls is here, then you can think about this as the derivative of the increase, right? Is the increase, the rate of increase of the ball. So if it's negative, that means that the tendency of this thing to decrease will be negative, right? So if you're here and this red curve is negative, then we will go to the left. If it's positive, then we will go to the right, okay? So even though 1/2 for the red curve, 1/2 is an equilibrium point, right? If we have 1/2, then this guy has the expectation 0, so we don't expect the rate to the proportion to change, but it's an unstable equilibrium because if you go just a little bit away, then it will pull you out, okay? And there are these two roots. And the process will be drawn to one of those, okay? Whereas in the high mutation rate regime, this is what happens. There's only one root, one equilibrium point, and that's actually a stable equilibrium point, okay? So here's what we get. So there's this constant here, alpha k. The important thing to know is that alpha 1 for the case of trees is 1. When we have 3 parents, then it's 3/2. And for large k, it's something like square root of k. And then there are 3 important regimes. The low rate of mutation, the medium rate of mutation, and this should be high. This is the high rate of mutation. So low means that we are far away from 1/2, more than 1/√k away from 1/2. For example, if k equals 3, then these 2 thresholds here at 1/6 and 1/3, okay? When k equals 1, then there's no low rate of mutation regime. This thing never happens, okay? So what happens in the low rate of mutation regime? Well, there are these 2 distinct roots far away from 1/2, right? These 2 guys, beta 1 and beta 2. And then the proportion of red balls will converge to one of those, okay? It can converge to either of them, and both of them will occur with positive probability. But what we can show that if the initial majority is blue, then it will be more likely to converge to the blue side. Okay, so this is very, very different, and that means that we will beat random guessing. This beta is when p is a constant and k is large. This is really, really close to 0 and 1. Okay, this is very different from what happened when k equals 1. This regime doesn't exist. When k equals 1, macroscopically the number of red and blue balls is always 1/2, asymptotically. Okay. Here it will be very far from 1/2. In the medium rate of mutation regime, Rn converges to 1/2. However, if initially Rk was smaller than 1/2, then with positive probability, this Rn will never cross 1/2. So it will always stay on the same side. And on that event, of course, we are better. If it crosses 1/2, then it's a random guess. So we do better than random guessing in this regime. And in the high rate of mutation regime, when we're really close to 1/2, then this Rn will cross 1/2 infinitely often, and we don't do better than random guessing. Okay? So this generalizes what we had for cake was 1 when we had only these 2, but that was somehow a much simpler problem because we had a nice linear process. Here the nonlinearity complicates things. Okay, this was my last slide. So there are many questions regarding this last problem that remain open. What is the asymptotic probability of error? Because the only thing that we study here is if we do better than random guessing or not. What is the optimum? What happens if we are allowed to look at the graph and not just count balls? So, for example, we know that if all the initial balls are red, then no matter what the mutation probability is, we can do better than random guessing by using the root estimation results. Okay, but the probability of error of that is not very well understood. And extensions to other models, such as for preferential attachment models, the high degrees help a lot. So in fact, everything is somehow these type of problems. Finding the root in these when we don't have a tree, then everything is easier for preferential attachment because the high degrees actually make it work. Here, the high degrees don't mean anything. So we have to work harder. But there are also nice geometric variants of these growing network models when there's some underlying geometry. Vertices are represented by, let's say, random points in some space, and then you attach to the closest point. These are called the online nearest neighbor trees, and there are many other nice extensions. Okay. Thank you for sticking around. That's all I wanted to say.
Questions?
Yeah.
I'm wondering if the computational complexity is ever sort of
Since we haven't done applications, it wasn't much of our concern. But so in all cases, you can have at least polynomial time algorithms. So for the centrality measures, Jordan centrality that can be computed on a tree that can be computed in linear time, basically. So that's really fast. These double cycles, we can do it in cubic time, which is, for large networks, that's not really good. So that's a good question. Can you do something that runs in linear time and then it's not trivial? That would be very nice to know. Yeah, so there are lots of nice questions there that we haven't really thought about. Yeah. Yeah?
You know of a preferential attachment or of any of these models where which does depend on them, where you can't do the constant?
Oh, that's a good question.
Something like trying to take, instead of taking the highest to the lowest,
Oh, yeah, sure. Okay, we can come up with or you can take a Galton-Watson tree, or something like that. Then you depends. You take a Galton-Watson tree with a Poisson distribution, then every vertex is equally likely to be the root. That's a very good question, and also something that as a statistician I'm worried about is that some of these methods are very model dependent. So Jordan centrality is nice because we know it works in several type of models, but is there something that's very robust? What are the good ones? So yeah.
The
Yes.
But when you check the results, I think that for preferential trees you have the optimal K, right?
Yes.
But for uniform trees you
We don't. So mathematically, it's hard. It seems to be harder, but it's when I said harder, then I meant that the required value of K is larger.
Okay.
It's in that sense, yeah.
I suppose you could ask something like, okay, so is this thing very special about being right at the start? Or if I point to the vertex and say, when did this arrive? You could say, oh, around root n or something.
Yeah.
Would that be possible, or is it completely different?
So we are working on a version of this. When we want to guess the arrival time of all the vertices at the same time. So the output of our estimator is a permutation of the vertices, and now we have some ways of comparing that to the truth, and so in some sense we can do something.
That sounds actually stronger than what I asked, in some sense.
But no, I don't think that implies of what you asked. That's also a very nice question. Yeah, when did this guy arrive? That's a good one. Yeah.
If instead of Qdex, you have something random, that you might be, something
Yeah,
like
yeah.
one, something like
Yeah.
that, guys, would it change too much?
I don't know. Nice. Nice. No, that's a very nice question. I don't know. Absolutely. Yeah, absolutely. When you have a random number of.
This doesn't change quite much. As soon as the probability of being at least 2 is positive, and then you sample from the same distribution of the number of ancestors.
Oh yeah. Okay. Yes. Yeah. That's right. Yeah.
So, yeah, maybe to answer Bob's question, I mean, there's a silly model, right, where you start with a point, but you grow at intervals. So adding points on the left or the right with equal probability.
Yeah.
Right, so that's going to have like sort of an fluctuation. You're not going to be able to. But that's okay.
Yeah, that's right. No, actually, these diffusion trees have been studied. So you start with an infinite D-ary tree, and in that case, it's known that you can find the root, and then everything is. But if D is 2, then you just have a line, and then you don't know. Yeah. So that's a nice.
What makes a model have a
Yeah.